Hello everyone and welcome to Seminar 6 of your course. As I did mention in my announcement on eClass, we plan to change the seminar delivery to make it a little more interactive and a whiteboard kind of experience. So let us get on with it straight away. Ideally, this would be done during the seminar sessions on Thursday and Friday as a real-time event, but for today, let's just go ahead with the recorded seminar. Let us start with question 1 of seminar 6. In this question, we are given a system that is equipped with a PI controller, that is a proportional integral controller. And we are told that the system is initially at steady state and that the error at steady state is equal to 0. And at time t equals 0, there is a step change in the measured variable. And the measured variable corresponds to the output variable y, of course. And we are told that the change in the measured variable is a step change of magnitude 2, as you can see. We are also told that the set point is unchanged. At t equals 0, all that changes is the measured variable. Furthermore, we are given the plot of the controller response in deviation form as a function of time. At p deviation is equal to 6 plus 1.2 times t, where t is time. And we are asked to find the values of the controller parameters, that is the gain of the controller as well as the integral time of the controller. I've written that as tau c. We will be referring to it as tau I in this seminar. So let us start off with solving question 1. And in this question, we begin by choosing the error term. E of t equals y set point minus the measured variable. This is also the controller input, if you remember. Now, since we have E of t equals 0 at time t equals 0, that is just before the step change was introduced, the system was at steady state, and we were told that steady state error is equal to 0. And therefore, when the system is at steady state with the controller in play, we can assume that the steady state measurement of y is equal to the set point given to the system. And therefore, E of t equals y set point minus y measured now becomes ym bar minus ymt. And this, as you can see, is just the negative y deviation, or y measured deviation, which we know to be a step input of magnitude 2. Therefore, let us start with proceeding with the time domain itself. We will see another method shortly, but when we consider the time domain, we start off with now looking at the controller output, now that we have said what the input is in terms of the step function. We have controller output equals kc times E of t plus integral between 0 to t times 1 over tau I, of course, E of tau d tau. And that is the general expression for a PA controller's output. So we can simplify this and substitute the error term as minus 2. We have substituted E of t equals minus 2 and not minus 2 times S of t, because for all t greater than 0, we have the value of E of t equals 2 according to this function. And similarly, when we put it in terms of the integral, you do want to put in the S of t, or rather S of tau there, in order to see how you will be performing your integration. But in essence, you are performing integration over minus 2. And the integral of minus 2, definite integral here, is going to be minus 2t. And we can further simplify it a little more, and we get the final expression for p deviation equals minus 2 kc plus minus 2 times kc over tau I times t. However, from the question, we already know another expression, the graph from the graph for p deviation. And from the question, we have that relation equals p deviation of t equals 6 plus 1.2 times t. And I'm actually going to just get rid of the brackets over here because, well, it's unnecessary. It's just a multiplication. It's not a function. I don't want you to get confused with that. So 1.2 times t. And from the general expression, substituting the error term, of course, we have minus 2kc plus minus 2kc over tau I times t. And as you can see from here on, it becomes a simple method of equating coefficients. You have minus 2kc equals 6, and therefore kc equals minus 3. And you have minus 2kc over tau I equals, 1.2, and therefore you have tau I equals 5. And these values constitute the final solution, which they have asked for, the controller parameters themselves, the controller gain and the integral time. And I mentioned that there is another method by which we can solve this, and that is to convert everything to the S domain and work with that, to work with the Laplace transforms rather than the time domain values. So let us see how to work with this problem in the Laplace domain or the S domain. We start off by first taking the controller output. No specific order over here. We just need to convert everything to to S domain. So we start off with controller output equals 6 plus 1.2 times t. And in order to get it into the S domain, you will have P of S equals 6 over S plus 1.2 over S squared. And how you get that is by taking the Laplace transform of P of t. And furthermore, you have the controller transfer function. Gc of S equals Kc times 1 plus 1 over tau is. And well, in this case, it's pretty simple to see what we want this to be. We just want it to be completely represented in the S domain, and we know that the controller transfer function equals output over input for the controller. Controller output in the S domain is P of S, input is E of S. Therefore, that's the final thing we need to obtain, E of S. And we get that by taking the Laplace transform of E of t in the deviation form. However, we know that E bar equals 0. That is given in the question, that steady state error is 0. Therefore, we now have E of S equals Laplace transform of E of t simply. No need for the deviation term anymore. And we have, that is the Laplace transform of the step function. So we finally have E deviation of S equals minus 2 over S. And now that we have everything in the S domain, all that we need to do is substitute it back into the expression for the controller transfer function. So we have Gc of S equals P of S, E of S, and therefore we have Kc plus Kc over tau is equals 6 over S plus 1.2 over S squared, completely over 2 minus 2 over S. So now we can just simplify this a little bit more, send the minus 2 over S term from the RHS over to the LHS, and that will give us Kc times 1 plus 1 over tau is times minus 2 over S equals 6 over S plus 1.2 over S squared. And a little bit more manipulation, we just say 6 over S plus 1.2 over S squared equals minus 2 Kc by S plus minus 2 Kc over tau I by S squared. And the same thing here, we equate coefficients of 1 over S and coefficient of 1 over S squared. So we have minus 2 Kc equals 6, giving Kc equals minus 3. And we have minus 2 Kc over tau I equals 1.2, and that gives us tau I equals 5. And hence we once again have the same values for the controller gain and integral time. And that is the solution. So you can just choose to work either with the time domain or the S domain as you are comfortable. Let us now move on to question 2. In this question, we are given a system block diagram. This represents a system that is a closed loop with controller GC, final control element GV, the measuring element GM, and the process itself depicted by GP. And we are told that the disturbance is given by GD. We're also given the transfer functions GC, GV, GM, GD, and GP. And for a unit step change in YSP, that is the set point, we are asked to determine the closed loop transfer function firstly, Y over YSP. We are also asked to determine the response when time t equals infinity or when t tends to infinity. We are asked to find the offset and whether or not the closed loop response is oscillatory. So let us start off with part 1 of the question, in which we are asked to find the closed loop transfer function for the system, and that is given by Y over YSP equals GC GV GP over 1 plus GC GV GP GM. And how we get a closed loop transfer function for a system between two variables is by taking the product of the transfer functions in the forward path between those two variables, in this case Y and YSP. And we divide that by 1 plus product of all the transfer functions in the feedback loop. So that gives us the closed loop transfer function. Let us start putting in the values of the transfer functions given to us in the question. So that equals 1 times 2 over s into s plus 1 divided by 1 plus 1 times 2 over s into s plus 1 times 1. And this can of course be written just as 4 over s into s plus 1 plus 4. And let's just open up the s into s plus 1 in the denominator. We would have 4 over s squared plus s plus 4. And to get it more typically in the form of a second order transfer function, you would have 1 over 1 by 4s squared plus 1 by 4s plus 1. And this is the solution for the closed loop transfer function that they have asked for in this question. So now we can proceed to part 2, in which they ask us what the response Y is when time equals infinity, or you can think of it as tending to infinity. And from the final limit theorem, we know that Y deviation of infinity equals limit s tending to 0 s times y of s in deviation form. And you should note that transfer functions are given between deviation form variables. So the above transfer function we have derived is in deviation form, even though we haven't specified it explicitly. And so we would just have limit s tends to 0, s times ysp of s in deviation form times the transfer function. It's just a simple cross multiplication from part A. And so you would have y of infinity equals limits s tending to 0, 1 over 1/4 s squared plus 1/4 s plus 1. And here all we need to do is substitute s equals 0 in the denominator. And that gives us 1 divided by 1/4 times 0 squared plus 1/4 times 0 plus 1. And so y at infinity equals 1. And this is the final solution for part B of the question. Now let us move on to part C. In part C, they ask us the offset. An offset is defined as the difference between the set point and the response at time t equals infinity. And we normally consider it in deviation form, of course. So we have YSP at infinity minus Y at infinity. Now, we are told over here that there is a step response or a step change, I'm sorry, in YSP. So we have 1 minus 1 equals 0. There is no offset with this form of a controller for this system for the step change in the set point. And that would be the final answer for part C. And finally, in part D, they ask us for the closed loop response and whether or not it is oscillatory. In order to find the nature of the closed loop response, we work with the characteristic equation of the system. And the characteristic equation for a closed loop system is equal to 1 plus GC, GV, GP, GM, basically the transfer functions in the feedback loop, equals 0. And so we have 1 plus 1 times 2 times 2 over s into s plus 1 times 1 equals 0. And you would have s squared plus s plus 4 equals 0. That's your characteristic equation. And upon solving, we get the poles or the roots of the characteristic equation as minus 1 plus or minus j root 15 over 2. And so, as you can see over here, both poles have non-zero imaginary parts. And if you remember from your previous seminars, we have seen that if the poles of the characteristic equation have non-zero imaginary parts, that the response will always be oscillatory. And that constitutes the final solution for question 2. So let's just mark off the solution there. Let me just actually go back and mark off the solution for offset as well. And that's it for question 2. Now let us proceed to question 3, the final question in the seminar. In this question, we are given an integrating system, also known as a pure capacity system. And the system is represented by Kp over S, and so is the disturbance in this case. We are given Gv equals 1 and Gm equals 1. And we are asked if we use a proportional only controller in this closed loop, will it eliminate offset when we have a step change in the set point, that is YSP? And will it eliminate offset for step change in disturbance, that is D? As you can see, we just have a schematic, a simple schematic of the closed loop here. So let us proceed to solving the question. Let us start off with part A of the question, in which we consider a step change in the set point, YSP, and whether or not in the previously shown closed loop, using a proportional only controller will eliminate offset or not. So we must find the closed loop transfer function using a proportional only controller first. So a proportional only or a P controller. We have Y of S over YSP of S equals 1 plus GCGV GP over 1 plus GCGV GP GM. And you have the forward path transfer functions. Actually, we don't have a 1 plus term in the numerator, so get rid of that. So you have Kc, which is the gain of a proportional only controller, times 1 times Kp over S plus. And so you have Y of S over YSP of S equals Kc Kp over S plus Kc Kp. And this is our closed loop transfer function. So now in order to find offset, we must first find the y at t equals infinity. And in order to do that, we consider a step change in set point, which is represented as y as p of s equals m over s. So we have y prime at infinity equals limit s tending to 0 s times y prime of s equals limit s tending to 0 s times m over s times kc kp over s plus kc kp. And we can just cancel out the s's over there in s and m over s. So you would get y prime at infinity equals limit s tending to 0 kc kp times m s plus kc kp equals m times kc kp over 0 plus kc kp, and so we are only left with y prime at infinity equals m. So now to calculate the offset, we have offset equals y set point at infinity minus y at infinity. And so that is m minus n equals 0. You must realize that offset, of course, is calculated in the time domain, as you can see over here. That's why it's m and not m over s. So we have the P controller, in this case, eliminates offset for this particular system for a step change in the set point. So now let us proceed to the final part of the question, which asks us whether this controller in this setup would eliminate offset when there is a step change in the disturbance variable given by D. So we have the closed loop transfer function. Using the P controller as before. We have y of s over ysp, sorry, it should be over d of s equals gd divided by 1 plus gc, gd, gp, gm. And it is only gd in the numerator because that is the only transfer function in the forward loop, in the forward path between y and d. So you have kp over s whole over 1 plus, well, kc times 1 times kp over s times 1. And let's move things around a little bit to get the transfer function. Y over d equals kp over s plus kc kp over s. And so you would have kp divided by s plus kc kp. So this is the transfer function that we obtain when between the output and the disturbance variable. And now we consider a step change in the disturbance, which is m over s. And we have the response of y at infinity equals, use the same final limit theorem in order to get limit s tending to 0 times s times m over s times kp over s plus kc kp. And now when we substitute s equals 0, we end up with m times kp over 0 plus kc kp. Cancel out the kp's in order to get m over kc. And now for this problem, we have offset equals y set point minus y, both at infinity. Remember that it is still set point. Offset always deals with the difference between set point and the actual response. So we have no longer have m because there is no step change in the set point in this case. There is a step change in the disturbance variable. So we have 0 minus m over kc equals minus m over kc. This is our new set point, which is no longer 0. So that means that the P controller in this case does not eliminate offset. For the system, for a step change in the disturbance variable. So let me just quickly go back to the previous solution and add in this detail. And here we have the final solution. So that brings us to the end of this seminar, and I hope you have all followed the questions in this seminar. As you can see, we've changed it up a little bit in order to go a bit more step by step in calculations as we write them out, so that hopefully when you watch this video, you're solving it along with me. So that's why I've tried to be as detailed as possible when I write it down. You are welcome to email us with any feedback over this format of seminar delivery and or any suggestions for improvement or changes. Just make sure to correspond with both Dr. Lee as well as the TAs on this. So thank you for joining on this video, and see you in the next seminar.